Welcome to the Deep Dive. Today, we are strapping in for, well, a pretty high-velocity mission, actually. Our listener, that's you've essentially been tasked with preparing a really essential audio guidebook. Think of yourself as a teaching assistant, creating a condensed manual for students who are about to dive into this cutting-edge natural language processing curriculum, the one famously guided by the human AI, Srinidhi Ranganathan.
Exactly. And our goal here is really about precision. This deep dive, it isn't just a summary. We're aiming for the distilled essence. We need to cut through all the noise and really provide those core nuggets of knowledge, those key insights. The idea is that anytime a student feels a bit stuck or just needs a quick, solid refresher on a tricky concept, this is the resource they reach for. We're basically building an on-demand mastery map.
And it's quite some map, isn't it? I mean, the material we're dealing with here fuses engineering, linguistics, even some high-level philosophy. This curriculum, it's not just teaching you how to, run Python scripts. It's positioning you, the listener, as one of the key thinkers who will actually design the communication protocols between humans and machine intelligence for the foreseeable future.
Absolutely. And if you look back at the history of AI, every major leap forward, think about the breakthrough that made Google search actually work, or the deep learning architectures that power models like ChatGPT. They were all fundamentally built on these very principles. So mastering this material is like understanding the source code of machine consciousness itself. Let's start with the big picture, the revolutionary vision that really drives this whole program.
Okay, so if we dig into the core intent, the main mission of this curriculum, it's actually quite profound. It's about forging, really, the first generation of technical leaders who can seamlessly bridge that gap. The gap between the inherent messiness, the complexity of human language, and the strict logic of machine intelligence. This is all about setting up the foundational language protocols for what comes next in human-computer interaction.
And crucially, it starts with philosophy, not just syntax. The course's unique approach really begins with a very tough question. How do we teach machines to genuinely understand human intention, human nuance? This forces students right from the start to think beyond just seeing language as a computation problem. Instead, they have to immerse themselves in this deep philosophical challenge. How do human language and machine consciousness converge? It encourages you to be an architect of AI, not just, a user of pre-built tools.
That distinction, architect versus user, that feels really key, especially when you compare this module to more, let's say, traditional or maybe generic NLP courses out there. There seem to be some clear differentiators here that make this material not just globally relevant, but also uniquely challenging for the students you're helping guide.
Definitely. The first one, and it's woven through absolutely every unit, is the intense focus on cross-cultural language processing. You see, standard NLP training often kind of assumes a simplified, standardized English structure. But the reality, particularly in diverse markets like India's, is way more complex. This curriculum tackles head-on the computational challenges of Indian languages and, importantly, multilingual realities.
And the practical implications of that are just massive. We're talking about morphologically rich languages, right? Where a single root, where you gave the example of the Hindi word for boy, but it can inflect into multiple forms like akarangora, or changing its grammatical role completely. So if your basic algorithms, the ones for tokenization and stemming, if they were just designed for English and don't account for this, well, the whole system just falls apart. Garbage in, garbage out.
Exactly. And then you've got the issue of multiple scripts. You might have Devanagari, Tamil, Arabic scripts all appearing in the same data set. Plus, the very common reality of code mixing or language mixing happens all the time in conversational text. Think about phrases like, let's go for shopping. The course trains you to build systems that are resilient to this kind of linguistic chaos. That's a critical skill for deploying AI effectively on a global scale.
Okay, that makes sense. And the second big differentiator you mentioned?
That's the ethical AI foundation.
Yeah.
And this isn't just, a single chapter tacked on at the end. Responsible development, bias detection, fairness, these are foundational concepts. They're built into the instruction right from day one.
Which is so important because these language models, they learn from basically everything humans have ever written, right?
Precisely, which means they inevitably absorb and can even amplify existing human prejudices. So the students, the people you're guiding, they are taught immediate proactive strategies, how to identify those biases within the models, how to mitigate them. It's about turning them into ethical leaders who really grasp the social impact of the algorithms they build.
And the third point, You said it was future-oriented.
Yes, fiercely future-oriented. We're not spending time optimizing yesterday's algorithms here. Every single unit, every concept, it's framed with applications for the 2030s in mind. This is about preparing you, the listener, for high-level roles. Think about domains like autonomous knowledge discovery, multimodal AI integration, maybe consulting roles that demand a strategic vision for AI policy down the line.
Okay, so summing up this first section for our teaching assistant listener, diving deep into these principles isn't just about landing immediate roles like a cross-cultural AI specialist, though that's certainly possible.
Right. It's also about the long game. It equips you for those future positions where you'll be shaping international standards, leading AI transformation in whole sectors that, frankly, haven't even started adopting these technologies widely yet.
All right, let's transition into the nuts and bolts then. How machines actually start to understand language. Beginning with Unit 1, language modeling. It's a 7-hour block, laying that groundwork for digital communication. Now, we know a language model predicts the next word, basically. But for someone aiming for mastery, for someone preparing this guidebook, what are the deeper nuances they really need to grasp here?
Well, prediction is the function, yes, but probability is the mechanism. The core takeaway isn't just what it does, but how it assigns those probabilities. Early models, they relied on n-grams, basically looking at the previous few words. Computationally simple, sure, but they run into problems quickly, like data sparsity. The course moves pretty fast from there into the architecture of neural language models. These learn much deeper contextual representations using things like attention mechanisms. That lets them look backward and forward across really long distances in a sentence.
And understanding that evolution seems crucial because it immediately brings up the main villain in NLP, doesn't it? Ambiguity. If a machine just relies on immediate probability, it completely misses the real meaning sometimes.
Exactly right. We all know that classic example, I saw a man with a telescope. Who has the telescope? But ambiguity goes much deeper. You have syntactic ambiguity, which is about sentence structure problems, and then semantic ambiguity, the meaning problem, like the bank was flooded. Is bank the financial place or the river edge? A human figures it out from context, but the machine, it has to use these massive context vectors to make that call.
Which brings us back to the course's focus on Indian language challenges. This seems technically vital here. So for you, the listener acting as a teaching assistant, you need to emphasize that standard n-gram models. They pretty much break down instantly in languages with flexible word order, like Hindi or Marathi, where context is often carried by markers on the words themselves, not just their position.
And that leads us perfectly into Unit 2, word level and syntactic analysis. Another 7 hours, this time dedicated to mastering the actual building blocks of language. It starts with tokenization.
Okay. Tokenization, breaking text into smaller units or tokens, we get that. But the key insight here for our master student, for you creating this guide, is probably understanding where standard tokenization fails, right? In English, we mostly just split by spaces. But what about languages like Chinese with no spaces, or that really complex code-mixed environment we discussed?
Yeah, standard methods won't work there. You need more advanced techniques. Things like byte pair encoding, BPE, or word piece algorithms. These are essential for the big transformer models. They create subword tokens. This helps handle words the model hasn't seen before, out of vocabulary or over V words, much more gracefully. And that's absolutely vital when you're dealing with rapidly changing slang or borrowed words, like in that let's go for shopping example.
Got it. Okay, after tokenization, the course really drills down on this critical difference between stemming and lemmatization. This isn't just about definitions, is it? It's an algorithmic trade-off.
Precisely. Stemming, as the course explains it, is the fast, kind of crude, rule-based approach. It often just chops off common endings like ings or ed-in. Students, and you as their guide, must know that while it's fast, may be useful for things like search indexing where small errors don't matter too much, it often leads to non-words, like your fly is becoming fly example. The course points to things like the Porter stemmer or Lancaster stemmer as examples of these speed-optimized but somewhat blunt tools.
And contrasting that with lemmatization, which is smarter.
Much smarter, yes.
Yeah.
It's context-aware. It actually needs linguistic knowledge, like a dictionary lookup, essentially. It often uses part-of-speech information, which we'll get to convert words back to their proper base form, their lemma. So better becomes good, or am, are, is all become be. It finds the meaningful root.
So the key insight for the teaching assistant, for you, is really the technical necessity of lemmatization in those morphologically rich languages.
Absolutely critical. Since one root word in Hindi or Tamil might have dozens of perfectly valid grammatical forms, Only lemmatization can correctly group them together for analysis. Stemming just isn't robust enough. It would treat all those forms as different words.
And this ties directly into Assignment 1, Task 1.3, doesn't it? That exercise where you have to compare stemming and lemmatization on tricky words like children or better. It's not just busy work. It's making sure you understand that accuracy versus speed trade-off and can justify why you'd pick one pre-processing technique over the other, depending on the job and the language complexity.
Exactly. And the final piece in Unit 2 is mastering part of speech, POS, tagging. So we label words with their grammatical role, noun, verb, adjective, and so on. It sounds simple, maybe, but it's absolutely indispensable for resolving ambiguity.
Yeah, the example, the EDT, quick AJ, brown JJ, fox and N, jumps V BZ makes it clear. The tags let the machine see the structure. But for our advanced audience, for you, the complexity probably comes in with, say, agglutinative languages, where words are formed by sticking lots of affixes together, making these really long, complex tokens.
That's right. It ramps up the tagging difficulty exponentially. It demands much more sophisticated taggers, often statistical ones like hidden Markov models or neural approaches like conditional random fields that are specifically fine-tuned for those kinds of linguistic structures. Mastering POS tagging, especially for diverse languages, is essential because it feeds directly into the kind of syntax analysis needed for the next unit.
Okay, so Units 1 and 2 gave the machine reading comprehension, in a sense. Unit 3, which focuses on extracting relations from text, feels like where that comprehension starts to turn into actual knowledge. This seems to be the mechanism that lets AI systems move beyond just processing data to actually generating insights. The course calls it the holy grail of AI.
Yeah. It really is. This unit is all about taking messy, unstructured text and imposing structure onto it. And the primary tool for that is named Entity Recognition, or NER. NER is basically sequence labeling. The system reads a sequence of tokens, like a sentence, and labels chunks of them based on predefined categories.
Yeah.
Person, organization, location, date, things like that.
Right. The example used is Apple Inc. was founded by Steve Jobs in Cupertino in 1976. The system sees Apple Inc. tagged as ORG, Steve Jobs as person, Cupertino as location, 1976 as date. For the course, and for you guiding students, the focus needs to be on training models that can recognize names even when they appear across different scripts. That requires really robust embedding strategies that can unify representations no matter what characters are used underneath.
Exactly. And once you've identified the entities, the next crucial step is relation extraction. It's not enough just to know these entities exist. We need to understand how they interact. This process identifies the specific types of relationships between pairs of entities.
So we're looking for things like founded by, linking an organization and a person, or maybe works for, linking a person and an organization, or headquartered in, company and location. This sounds like it involves training classifiers, probably using those POS tags and maybe dependency information from Unit 2 to figure out the semantic link between the entities.
That's exactly right. And when you start aggregating all these extracted entities, the relationships between them, you begin to form a knowledge graph. KG. You should think of a knowledge graph as this giant, interconnected web of facts. It's the kind of intelligence that powers systems like Google's knowledge graph or sophisticated decision-making tools within large companies.
And the course seems to push into quite advanced KG capabilities, specifically mentioning temporal relationship tracking. What's that about?
Yeah, that's important. It means that KG doesn't just store static facts like X is CEO of Y. It tracks how relationships change over time. So it can tell you who is CEO of a company when a specific event happened. This ensures the knowledge base stays historically accurate and relevant, which is critical for many analyses.
Okay, and the course highlights some breakthrough methodologies here.
It does. One is cross-document synthesis. This is really powerful. It's the ability to connect entities and relationships that might be mentioned separately across potentially millions of different documents. This allows AI to start formulating novel hypotheses that no single human could possibly piece together.
Could you give an example of that?
Sure. Imagine connecting, say, a specific gene mutation mentioned in a research paper from 2010 with a particular drug side effect reported in a completely different clinical trial paper from 2020. A human researcher might never stumble across both pieces of information and make the link, but a KG, systematically analyzing connections across documents, could potentially generate and even validate that hypothesis.
Wow, okay. And the other critical methodology mentioned is causal relationship modeling.
Yes, and this is arguably even harder. Most statistical analysis just finds correlation. A and B tend to happen together. Causal modeling, however, tries to determine if A actually caused B. This is exponentially more difficult. It requires specialized learning techniques, trying to rule out confounding variables and spurious correlations to get closer to actual causation.
And mastering that is obviously essential for really high-stakes applications, like accelerating medical research, where proving causation is everything, or maybe investment intelligence, trying to find the real drivers of market moves, not just noise.
Precisely. It moves from just describing the world to starting to understand its underlying mechanics.
Okay, all that theory is great, but it really comes alive when you see it applied in a large-scale, real-world situation. The Ecomart customer review analysis case study sounds like it perfectly shows the kind of financial and operational power you get from mastering units 1, 2, and 3.
Oh, absolutely. Ecomart, this e-commerce giant, they're getting something like 10,000 customer reviews every single day. And they face this classic problem of scale. Their old process, entirely manual. Maybe someone could glance at 200 or 300 reviews a day. They were essentially flying blind when it came to emerging issues or trends in customer feedback.
And that anecdote you mentioned really drives it home, the smartphone case example.
Yeah, it's a stark one. They had a popular smartphone case, and over about 3 weeks, 50-plus reviews came in mentioning it was flimsy or fragile. But because spotting issues depended on a human scanning report slowly, the pattern was completely missed. Until, that is, a negative review video went viral. Boom, a 40% sales drop almost overnight. That detection delay, those 2 to 3 weeks, cost them significantly.
Wow, 2 to 3 weeks versus spotting it potentially much faster with NLP. So the solution described in the course, how did it tackle this?
It's built on a pretty rigorous 5-component architecture. Something that students, and you as their TA, need to be able to understand and ideally replicate.
Okay, let's break it down. Component 1 must be data collection, right? Getting the reviews in.
Yep. High-volume API integration, secure web scraping protocols, getting that raw data reliably. Then component 2, the text pre-processing pipeline. This is where all that hard work from Unit 2 pays off. Careful tokenization, robust limmatization, which is critical for handling messy user language, noise removal, stop words, the whole package.
Right. Then component 3, that's the analysis engine.
That's the heavy lifting, exactly. This is where the techniques from Unit 3 get deployed. So not just overall sentiment scoring, positive, negative, neutral, but much more granular aspect-based sentiment analysis. This means the system understands that, okay, maybe the review overall is positive, but the sentiment specifically about battery life is negative. That lets product managers pinpoint exact issues, not just vague feelings.
Very cool. Component 4.
Component 4 is the brain, you could say.
Yeah.
The intelligence layer. This is responsible for spotting trends over time and, critically, alert generation. And finally, component 5 is the user-facing bit, the reporting dashboard for real-time visualizations.
And the alert system sounds key to the whole thing working fast. What kind of thresholds did they use?
They define very specific triggers. For example, any product seeing a 30% spike in negative sentiment within just 24 hours. Or a sustained drop in the average rating, say by 0.5 point. Or maybe accumulating 5 or more mentions of really critical keywords like broken, defective, or crucially, unsafe. Any of those would immediately trigger a high priority alert to the relevant team.
And the results, the numbers must have been dramatic.
Absolutely staggering. Review analysis capacity went from that 200, 300 per day manually to over 10,000 per day automatically. But the crucial number, issue detection time, it plummeted from those painful 2 to 3 weeks down to just 2 to 4 hours.
Hours. That's transformative.
It had immediate financial impact. Their customer satisfaction score, which we know is tied directly to future sales and customer loyalty, it improved by 28%.
Yeah.
Jumped from a mediocre 3.2 out of 5 to a much healthier 4.1.
And there was that specific success story, the Bluetooth speaker.
Yeah, that's the ultimate validation. The NLP system started picking up a pattern across multiple reviews mentioning overheating and even burning smell. The alert hit the product team's dashboard within just 6 hours of the first few mentions coming in.
6 hours.
Because of that rapid alert, the team was able to investigate and confirm a genuine manufacturing defect by day 2. Critically, they stopped production and initiated a precautionary inventory recall by day 3. This proactive move almost certainly avoided a major safety incident, maybe even lawsuits. The estimated cost saving, around $2 million in potential recall and liability costs, all because of 6 hours of AI vigilance instead of 3 weeks of slow manual review.
That's incredible ROI. And the case study also pushes students to handle other real-world data problems like fake reviews.
Yes, it does. They tackled fake review detection. The system learned to analyze patterns often associated with fake reviews, things like excessive capitalization, way too much punctuation, maybe repetitive phrasing. Using these patterns, it assigned a suspicion score, and they got it working with nearly 90% accuracy in flagging potentially bogus reviews.
And multilingual reviews. That must be huge for a global retailer.
Absolutely critical. About a quarter of EcoMart's reviews weren't in English. So the solution integrated the Google Translate API. This ensured that reviews in regional Indian languages or other major global languages were still processed quickly and accurately. No customer voice got ignored just because of the language they used.
Okay, moving into the more advanced parts of the curriculum now. Units 4 and 5 seem focused entirely on the future capabilities needed for real strategic AI leadership. Unit 4 zeroes in on evaluating self-explanations. This is the domain of explainable artificial intelligence, XAI, right?
That's right. And the driver here is simple. We just can't tolerate black box AI anymore. Not when AI is making high-stakes decisions. Things like proving loans, suggesting medical diagnoses, assessing legal risks. The systems have to be able to justify their reasoning. This is increasingly being driven by regulations demanding transparency, accountability, auditability.
So the goal of this unit for you guiding students is teaching them how to build AI systems that are, well, transparent enough to actually teach other AI systems, and maybe more importantly, transparent enough to explain complex reasoning to humans who aren't AI experts, like a doctor or a financial regulator.
Exactly. It involves mastering techniques that can actually highlight which specific features or data points led to a particular outcome. For instance, that medical diagnosis system we mentioned. It needs to be able to show the doctor precisely which combination of symptoms and lab results pointed towards its conclusion. This ensures the human expert stays in control, can understand the reasoning, and can challenge the machine if needed.
So this really positions the listener, the TA, for crucial roles in things like AI compliance and governance down the line. You're learning to build the infrastructure that makes AI trustworthy and compliant. Creating tools like, say, educational AI tutors that can transparently show why they're adapting their teaching method based on a student's specific weaknesses.
Precisely. Then we hit Unit 5, Information Retrieval Post-Google World. And the key takeaway here, for you guiding others, is that traditional keyword-based search. It's basically on its way out.
Why is that? What's the fundamental problem?
Because simple keyword search just fails to capture context, intent, and nuance. It's too literal. If you type, say, best movie about flying without planes, a traditional search engine might just prioritize results that happen to have the words flying and planes close together frequently. It doesn't understand the concept you're asking about.
Ah, I see. So the course emphasizes the next generation of approaches.
Yes, starting with semantic search. This leans heavily on those vector embeddings we talked about, learned representations of meaning. The goal is to match the intent of your query to the meaning of the documents, even if the exact keywords don't match up perfectly. Mastering this means getting comfortable with vector database technologies.
And it goes beyond text too, right? Multimodal retrieval.
Absolutely. The future of information retrieval isn't just text. AI needs to be able to query and synthesize information from text, images, audio, and video all at once. Imagine searching for a specific historical event and getting back not just text articles, but also relevant video clips, timestamped to the key moments, maybe automatically contextualized with audio transcripts.
That sounds powerful. And the final piece was personalized knowledge discovery.
Right. This moves beyond just giving everyone the same generic set of search results. It aims for results highly tuned to your specific profile, your search history, your current project or goals. This requires systems that can make pretty advanced inferences about what you actually need, not just what you typed into the search box.
And you mentioned earlier that the genius of this curriculum is how integrated it is. It's not just 5 separate units in isolation.
Not at all. It's designed as a pipeline. Think about it. Unit 2's high-quality lemmatization is what enables Unit 3's accurate relation extraction. You need good building blocks for complex structures. And Unit 4's demand for transparency and explainability is what makes the advanced, personalized search in Unit 5 trustworthy and auditable. You need to know why this system is showing you certain results.
Yeah.
Everything connects to build a reliable, understandable system.
Looking at the career path this sets people up for, the short-term roles, say 2025, 2027, seem pretty clear. NLP optimization specialists, those cross-cultural AI experts we discussed, maybe diagnostic engineers who can figure out why an AI pipeline is failing.
Exactly. Those are the immediate needs. But the truly transformative roles are the ones emerging in the 2030s. We're anticipating the widespread adoption of multimodal AI systems integrating voice, vision, maybe even emotion analysis, probably by around 2028. This means today's NLP specialists will increasingly need skills in image recognition, audio processing. It's a necessary convergence.
And translation technology.
We're also projecting universal translation, real-time context-perfect translation between basically any language pair, crucially maintaining cultural nuance becoming viable maybe by 2027. And looking even further out, the curriculum is designed to prepare students for the eventual shift towards quantum-enhanced NLP, likely in the 2030s.
Yeah.
That could unlock currently theoretical speeds for learning and complex pattern recognition.
Okay, to wrap up our guidebook creation mission, let's do a rapid-fire review of the essential definitions and practical tools that anyone mastering this needs to have down cold. This is like the pocket dictionary for the advanced practitioner you're helping create.
All right, first up, a crucial distinction. BERT versus GPT. You have to nail this. BERT, that stands for bidirectional encoder representations from transformers. The key word is bidirectional. It reads the whole sentence at once before making a decision. It's an encoder, optimized for understanding tasks like classification, sequence labeling, like NER, GPK generative pre-trained transformer. This is typically decoder only. It reads sequentially, left to right. It's optimized for writing, for completion, for generation. So, broadly, BERT for analysis, GPT for creation.
Got it. Next, those foundational ways of representing text numerically. BOW, bag of words.
Simplest concept. Represent a text just by counting how often each word appears. Completely ignores grammar, word order, context. Conceptually easy, but contextually blind.
Okay. Building on that, TF-IDF, term frequency inverse document frequency. Essential for search, you said.
Absolutely. It measures how important a word is to a specific document within a larger collection. It balances how often the word appears in that one document, term frequency, against how rare that word is across all the documents, inverse document frequency. This stops super common words like the or and from overwhelming the importance scores.
Makes sense. And finally, cosine similarity. Why is this the go-to measure?
Right. It measures the angle between two document vectors in that high-dimensional meaning space created by embeddings. The key thing for you as the TA to explain is why we use cosine similarity instead of something simpler like Euclidean distance. In these high-dimensional spaces, the direction or orientation of the vectors, representing meaning, matters much more than their absolute distance apart. A score of 1 means identical direction, identical meaning.
Okay, understanding the concepts is one thing, but you need the right tools. The course focuses on 3 key Python libraries, plus the big one for modern models.
That's right. First, NLTK, Natural Language Toolkit. This is the classic pedagogical tool. It's fantastic for learning, for research, because it really exposes the underlying algorithms, lets you customize things heavily, but notoriously slow for actual production use.
Okay.
Second, Spacey. This is your industrial strength workhorse. Highly optimized CPython underneath, extremely fast, built from the ground up for production deployment. It comes with efficient pre-trained pipelines for many languages. It's the practical choice if you were building something like that Ecomart system for real.
And the third library.
TextBlob. Think of this as the lightweight option. It provides really simple, high-level APIs for basic tasks, quick sentiment analysis, some grammatical processing, great for rapid prototyping or smaller, less demanding tasks. And then, underpinning almost all current state-of-the-art work, especially with large models, is the Hugging Face Transformers library. This gives you relatively easy plug-and-play access to implementations of complex architectures like BERT and GPT and thousands of pre-trained models.
And the assignments are where the rubber really meets the road, testing mastery as students progress.
Absolutely. They're designed very intentionally to ramp up complexity.
So assignment 1 is that beginner's hurdle, right? Making sure you've got the basics of the Unit 2 pre-processing pipeline down. Cleaning text, removing stop words, and critically doing that comparison exercise, seeing the crude speed of stemming versus the precise accuracy of lemmatization firsthand.
Exactly. Then assignment 3 is the intermediate test, focusing on extraction skills from Unit 3. Students use Spacey first to do standard NER on real news articles, but then it pushes them further into custom entity recognition. They have to write complex, regular expressions rejects basically from scratch, to pull out highly structured data like phone numbers, email addresses, URLs, maybe hashtags, from messy, noisy text like social media posts.
Okay, and assignment 5 sounds like the advanced challenge, really testing information retrieval mastery from Unit 5.
It is. The really deep dive there is the requirement to implement the core TF-IDF algorithm from scratch. No just importing a library function. You, the student, have to understand and code the full mathematics, the tokenization, the term counting, calculating document frequencies, doing the inverse weighting, the whole 9 yards.
And using that custom TF-IDF.
Using their own implementation, they then have to build a functional mini search engine. This isn't trivial. It requires implementing complex search logic, Boolean search, so handling A and D or R not operators in queries, phrase search, making sure words appear in the exact sequence requested, and wildcard search, allowing searches with partial words using asterisks. Completing that task really proves holistic understanding and capability.
And it all culminates in the final project, where students choose a path to really solidify their role as a creator.
Exactly. They get options like developing a comprehensive chatbot, building a robust news article analyzer that uses classification and maybe relation extraction, or deploying a social media sentiment monitor that essentially replicates the sophisticated alert system from the EcoMart case study. It's about building something substantial. Hashtag tag out, tag outro.
Well, this deep dive really confirms it. The knowledge packed into this curriculum, from understanding those subtle algorithmic trade-offs in lemmatization right up to the complex architecture of transformer models, it genuinely delivers on that promise the course makes, turning the dedicated learner, the person you're guiding, into what they call a 100x professional.
Yeah, and that exponential boost, that 100x factor, it isn't just about being able to use the AI tools faster. It's fundamentally about diagnostic ability. When a complex NLP model inevitably fails or gives weird results in a real production environment, you, having mastered this, won't just treat it like an impenetrable black box. You'll have the deep understanding to actually diagnose the problem. Is it a subtle tokenization error, an ambiguity the POS tagger missed, or maybe a systemic bias creeping in from the relation extraction training data? You can pinpoint the failure.
And you really are standing in a unique historical position, aren't you? The listener guiding others through this. You're part of potentially the last generation that will need human instructors to fully synthesize and explain these foundational principles from the ground up. And at the same time, you're the very first generation truly equipped with the knowledge to build, train, and strategically guide the next wave of machine intelligence. You are, in a very real sense, the bridge between accumulated human knowledge and emerging AI.
That mastery brings with it a significant responsibility, a powerful mandate. You need to use this knowledge ethically. You need to share your expertise to help raise AI literacy more broadly. And you need to pioneer responsible, globally relevant applications. The era of just passively consuming AI tools developed by others, that's rapidly drawing to a close.
It feels like the window of opportunity to be the creator, to be the architect, the strategic leader who actually designs the fundamental communication language between humans and AI for the 2030s. That window is wide open right now, but it's closing fast. These pioneering opportunities, they'll largely be claimed within the next decade or so.
So the choice is laid bare by engaging with this curriculum, by mastering this material. Will you, the listener, remain a passive user of systems that others have designed? Or will you seize this unique historical moment to become an active creator, an indispensable architect, and a responsible leader shaping the AI-powered future? The path to creation, to leadership, it starts with mastering this knowledge today.